Hello everyone, welcome to the third tutorial of MT203 Matlab session. And in this session, we'll be looking into advanced symbolic math and some numerical calculus as well as quiver plotting in Matlab. And the first part is some advanced symbolic math. We already know we can create symbolic variables by sims, for example, x and y. And now we can produce a function based on that. For example, we can say fxy. So f is your function name, right? fxy equals to, say, 3 times x minus 4 times y. And in this case, we will have a function called f, where fxy equals to f times x minus 4 times y. And notice that this f is also a same function here. You can find the value here is 1 times 1, same function, symbolic function. And based on that, you can always pass into some numbers to that symbolic function, say f, say 3, and the second argument to 3, f33 is minus 3. Because if you substitute the 3 in x, the 3 in y, you can always get minus 3. And further on, you can calculate the partial derivative of that symbolic function, right? It's very useful in week and fifth week's content. We can say the f prime of x equals to diff. Here, this is the function f, and here is a variable we're trying to differentiate it on. So here we do partial differentiation of the f with respect to x is 3. And further on, you can do f prime y of diff, here change to y, we'll get it as minus 4. So this will be very useful in finding the partial derivatives of any symbolic function. Further on, you can plot symbolic function as well. Clear everything, let's create a new symbolic variable, same as x. And now we have the fx equals to x squared plus 2 times x plus 1. And now let's create a figure. So figure 1, we can create a figure here, and now we're trying to plot it on that figure, right? So we can plot it on that figure based on f plot f. Here, this is a figure we just plotted. Can specify the range or the domain of the figure. We can do f plot. We can move around with that, say, negative 100 to 100. We can move on that figure with a new one, right? We can move on with a new one. We can always do that with 3D plotting as well. Here we use fplot f. We can use fplot 3D to plotting the parametric equations as well. So say we define another one, sims t, and now we already use the previous version, xt equals to cosine t. This is very useful since it's exactly the same. It's very similar to what you need to write down in your paper, right? When you're trying to solve equations or trying to write down the parametric form of curvature is exact same for the symbolic functions in Matlab. So here we do sine t. Notice that when we create yt here, we create a new symbolic function with respect to t, right? And now further on, we create zt. Let's create something very interesting. Let's say zt equals to tangent t. And let's do a figure. Well, I don't know what the figure will be exactly look like, but let's do figure 1. This is a figure we just created, but we'll cover that figure up with a new plot. F plot. Here we need to specify 3 since we're in 3D, and now we have x, y, as well as z. Let's find out, what does it look like. Oh, it looks like something. Let's look like this. Well, it's a very interesting plot. Okay, it's a very interesting plot. Similarly, you can specify the range of the t as well. Okay, since you can always plot a segment of curvature based on specify the range of the t, right? Specifying the range of the parametric equation. Multidimensional symbolic calculus. So multi-dimensional symbolic calculus, for example, we already introduced how to use partial derivatives over there, but we can do further, right? We do same x and y. X and y, so f here x and y. Now that's equals to 3 times x squared minus 2 times y triple. And here it is a function of x and y. We can taking partial derivatives using diff, right? We can using partial derivatives, and we can also take in partial integrals. For example, given saying df dy equals to diff f and y. So this is the here typo. It should be f and y. Okay, and we can calculate the partial derivatives of that original function, and based on that, we can also do a partial integral, say int of f based on dy equals to integral of f, and here let's say df dy df dy. Oh, it should be df dy based on y dimension, right? Based on y dimension. Now we have the df dy integral based on y dimension. We can further do another one. Say this is a f, this is a 2D function with respect to x and y. We can further integral of that. We can say this is int f, this is y. We can find the final form of the integral. Okay, this is taking partial integral. And calculate the gradient. There's a gradient, built-in gradient function of Matlab. So we can find gradient of the function f. It is a vector, right? It is a vector over x and y. It is a vector. And another very useful thing to we can use in Matlab is to plotting the vector fields using quiver. So Matlab allows us to plot vector fields in 2D using the built-in function quiver, and we can find the function quiver function by help quiver, and it plots velocity vectors as arrows with components u and v at the points x and y. So the matrices x, y, u, v must all be the same size and contain corresponding position and velocity components. So x and y can be vectors to specify the uniform grid. Quiver automatically scales the arrows to fit within the grid. So it's very obvious. Here's an example from the built-in Matlab. We can plot a very simple idea of this. So let's do quiver. Let's say 3, 4, 5, and 6. So since we need to pass in 4 arguments, right? So we just do 3, 4, and 5, and 6, and they are just single floating number. And after that, we find our plot. It's just a very simple like this. And notice that since I previously added a subplot command, right? I added a subplot command before, although I already cleared it. So this part is a subplot. The figure on the upper left. Okay, so this is subplot 221, and the starting point is 3 and 4, right? So this is a 3 and this is a 4. So this is the starting point of the vector, and 5 and 6 corresponding to the added vector. So starting from 3 and 4, the 3 added 5 becomes 8, and 4 added 6 becomes 10. So it is a vector pointing from 3 and 4 to 8 and 10. This is a single vector, and how do we plot a vector field? Well, we just need to supply Matlab with one vector for every point we care about. So for every point, you consider there's a scatter of points over there, and for every point, we'll provide it or assign a vector for that point. Then we can plot a vector field. For example, based on the brief example from the student manual, we can plot the gravitational force around the body of mass of m. For example, let's say t equals to line space. Here, let's do -1 e4 to 1 e4, let's say 50 points. Let's let the t equals to 0 becomes nothing, okay, becomes nothing. And we have the x and y equals to mesh grade of t, and we have g equals to 6.67 e minus 11, and we have m2 equals to 6 e24, and further on we have the distance is x squared plus y squared times 1.5. Squared 1.5, and the force of that is of course based on the physics. We have something like this. Furthermore, we have Fy. Here I need to change this to y. And now we plot the quiver x and y and fx and fy. So remember, before we have four arguments, right? 4 arguments: x, y, u, v. X corresponding the starting point of the x-axis, y is the starting point of any vector in y-axis. So here x and y should be in a similar shape, corresponding to the starting point of the vectors. And the u and v are corresponding to the form of the vector starting from x and y axis. So notice that the gravitational force is way higher near the center of the Earth than inside of it. So we'll have to zoom in to see the larger vectors. So we can do this plot before this plot. I wanted to plot it in this part, okay? In this part. So what I can do is subplot. Here is 2, 2, and 4, okay? Let's save it as quiver plot, and we'll run it. Undefined. Oh, here I should change the name as well. Okay, I should change the name, and then let's run it. And after run it, we'll find, oh, here there's a nice plot. And notice that we mentioned that we have to zoom in to see the larger values. We can zoom in further, zoom in. Okay, and the reason why we have to make the t, the number of t here, t equals to 0 here, as nothing because we're trying to move it. Because once we have x and y are 0, there will be some error when we calculate d, and also trying to divide it by 0. Okay, so that's the reason why we added this command here. And let's clear everything. Okay, let's move on to the final part of numerical optimization. So in many cases, other than calculating a certain solution to a function, we also always wanted to find the minimum. What's the point that a function reaches its minimum as well as maximum? Let's do with a very simple function. Say we already have it, right? We already have it. Or we already have a function called fun function, and it's a parabolic or quads function. It's x squared, right? We already know the minimum value of that function is when x equals to 0, and we can find the minimum using numerical solvers by x and y. This is the output equals to fmin search. So this is a function name, fmin search, and remember the first argument, since fun function is a function, we need to passing as a function. So at here fun function 1. Now the solver, of course, is trying to solve x and y to find when will be the appropriate x and y that reaches the minimum of the x. Here we got minus 8.8 e minus 16, which is very, very close to 0. Okay, very, very close to the final solution. Again, in many cases, you can use fmin search on many other equations or functions. However, similar to previously I have solved, the fmin search is heavily dependent on your initial guess. Always find the maximum of a function by adding a minus of the original function and then apply fmin search on that as well. And for fmin search for multivariable functions, you can do something like this. Let's try to change the fun function as z equals to fun function x and y. Let's change it where we have z equals to x. Oh, here there's a small thing. Here's a small thing that it doesn't work. But I'll show you. I'll show you later. Let's define this first. So x squared plus y squared. So we already defined a fun function that's passing two arguments were x and y, and the result of it is stored as z equals to x squared and y squared. Let's just try this. Let's just try. Let's do fmin search based on that. So we do v and z. So this is our final output where the output is stored, and fmin search, and it expected to pass in a function where we call this function fun function, and the initial guess we're passing as 1 1, which is an array, and of course it will report an error. It reports an error because this 1 1 are the arguments, right? These are only one arguments because it's an array. However, the fun function expected two arguments, right? It expected two arguments. Let's try different things. Say the fun func 1 and 1. Here it says argument 3 must be an option structure. Let's say why, because we can do help fmin search. We find that the argument is function f, the function as the first argument, x0 as the second argument. That is to say, your initial guess have to be stored in single vector in second arguments, and the third argument is options. And how do we change that? How do we do that? Using multivariable functions. We can still pass in single function x. However, this x is no longer standing for a constant. It should be a it should be a vector. And in here, it should be x1, and the second one is x2, right? So in here, this is a vector, and this is the first element of the vector, this is the second element of the vector, and z is the final function. And let's do that again. Let's do this. Now the fun function only requires only one argument, and the passing one argument of 1, 1. Let's try again, and obviously it worked. It worked. So notice that when you're trying to do the fmin search on the multivariable functions, you always need to define, and notice that you always need to define your fun function, which requires only one argument. However, you need to specify which element of the vector is in that function. Okay, that's it for the third tutorial of MTE-203. And for now, all of the MTE Matlab tutorials are finished, and I hope you have a wonderful experience in MTE-203 study, and also have fun in your projects.